Sounds good.
Okay, so I guess I started.
All right. So, hello everyone. My name is Jun Wu from the University of Illinois at Urbana-Champaign, and today I would like to share our recent work titled Personalized Federated Learning with Parameter Propagation. And for this talk, I would like to share this paper from the following aspects. First of all, I would like to provide some background regarding personalized federated learning, and then introduce the proposed method in this paper. And then I will provide some experimental result to evaluate the proposed method, and followed by more discussion on this topic, especially on the trustworthy transfer learning. So we see that federated learning is a learning framework that multiple clients can collaborate with each other to solve a machine learning problem. And this can be done with the help of a central server. And in this process, the key point is that each client's raw data can only be stored locally. That means the raw data in each client cannot be shared with other client or the central server. This learning framework has been applied in multiple real-world applications, like the mobile keyboard prediction, the healthcare analysis. And this is a very popular federated learning framework with 4 different steps. We say that for the first step, each client will update the parameters with respect to the provided local data. And then each client will upload the model parameters or parameter updates to the central server, so that the central server will have the chance to aggregate the received knowledge, the received parameters in this case, to form a global model. And finally, the central server will send the global model parameters back to each client. Those 4 steps will be repeated until we got a converged global model. But more recently, it's also shown that this federated learning framework can not perform well, especially when local clients have different data distributions. So to handle the heterogeneity issues, a new learning framework, the personalized federated learning framework, is proposed. And the goal of personalized federated learning is to learn a personalized model for each local client, so that even though the local clients from different, the local clients will have the chance to share some knowledge, but it's not required that they have the identical models. So in this paper, we would like to understand this personalized federated learning framework from the transfer learning perspective, so that we can take any client as the target domain, say client K in this case. Client K can be any client within the federated learning framework, and all the other clients as the source domain. So finally, for this target client K, the goal is to use the source knowledge from other domains for other clients to improve the prediction performance. And the question is that whether the transferred knowledge from other clients from other domains can help this target client improve the prediction performance. We will see what happens. And in this transfer learning perspective, we will see that each client will have 2 options. The first one is the local training. That means each client can just update the model parameters with respect to its own local data without sharing any knowledge, with other clients. And the second option is to participate in the federated training. In this process, in this personalized federated learning framework, each target client K will have the chance to receive some relevant knowledge, say the source knowledge in this case, from other clients. So the question is that whether the received knowledge, the transferred knowledge from other client can help improve the prediction performance on this target client K. If not, say like the transferred knowledge has a negative impact on the target model. This phenomenon we call negative transfer in the transfer learning field. And the first question is that whether negative transfer happens in existing personalized federated learning algorithms. So to answer this question, we conduct a very simple example. Like here on the left-hand side, we can see that we use 4 different clients with different number of training samples, and then test whether the negative transfer happened in some existing personalized federated algorithm, like the Fed averaging, the LG Fed averaging, and other models. So first of all, we report the accuracy, the prediction accuracy on the testing data set for each client using the local training model. The local means that each client will just train the local model with respect to its own data without sharing any knowledge, without participating in the federated training. And next, we also report the result using the federated learning or personalized federated learning models. We see that on average, if we just check the average accuracy, basically most of the personalized federated learning models can help improve the model performance. But if we check the accuracy for each client, we will find that not every client can benefit from this federated training. The red number indicates that the negative transfer phenomena happened for some clients, like for the popular federated learning, personalized federated learning algorithm, the Ditto method, we see that for client 1, client 2, and client 4, the negative transfer happened. So the goal of this paper is to avoid such negative transfer when we use the personalized federated learning framework. So here is the objective function of our proposed method in this paper. The algorithm name is the federated parameter propagation, or Fedora for short. And from this objective function, we can see that it has 3 key components. The first component is the local training, basically corresponding to the supervised loss with respect to the local training data in each client. Well, the second component is the approximation regularization. In this process, in addition to the local parameter theta k for the client k, here we introduce another parameter theta head k as the auxiliary model parameters stored in the central server. And this approximation regularization is to guarantee that the local model parameter theta k is going to be approximated by the auxiliary model parameters stored in the central server. Well, the third term corresponding to the distributional regularization, the motivation behind this term is that if 2 clients share similar data distributions, it's more likely to share the similar auxiliary model parameters. And this data distribution similarity can be just calculated with the local data stored in the local client, and we will share how to calculate the distributional similarity in the follow-up slides. And so the basic motivation behind this proposed method, behind this Fedora, is that we can guarantee that if 2 clients share similar share similar data distributions, they will have the similar model parameters for the personalized federated learning. And if we look into this objective function, say like how to optimize the 2 different types of model parameters, theta k and theta head k, we will see what happened for local client update and global server update. So like for the client update, we can fix the theta head k, which corresponding to the received knowledge from the central server for this client k. And after receiving the source knowledge theta head k from the central server, this target client k will have the chance to update its own local model parameter theta k, and we see that is corresponding to a regularized supervised loss. And the second regularization will be guaranteed that the updated model parameters can be approximated by the received knowledge. Well, for the second component, for the server update, that means each local client will upload its own local parameter theta k to the central server, so that the central server will have the chance to update the auxiliary model parameters theta head k. In this process, we say that it's corresponding to two terms. The first one is to guarantee that for the central server, the received local parameters theta k can be similar to the auxiliary model parameters. Well, the second term corresponding to like the motivation that if two clients have similar data distributions, finally, we hope that they have similar auxiliary model parameters. And with these two key components, we will see like similar to the learning frameworks we showed before. In this training process, in our case, we also have 4 different steps. Like for the client update, we will update the model parameters theta k for each client k. And then this client k will upload the model parameters or parameter updates to the central server, so the central server will do the aggregation step. And finally, the aggregated, the updated auxiliary model parameters, theta head k will be sent back to the client k. And next, I will show more details about how those, especially how the client update and server update will be taken in our training process. Well, before we running the personalized federated learning algorithm, first of all, we would like to calculate the distributional similarity between any two clients. Like, as we mentioned before, it's required that if two clients share similar data distributions, they are more likely to have the similar auxiliary model parameters. So here is the method we used for calculating the distributional similarity for any two clients. First of all, for each local client, we can conduct the standard SVD to get the orthogonal subspace to indicate the features, subspace features for this client. And then this client will upload this subspace representation to the central server. So the central server will calculate, first of all, calculate the principal angles between any two clients, like corresponding to any two received subspace. And next, the distributional similarity between any two clients, say client K and K prime, will be defined over the difference over the principal angles. With this method, we can calculate the similarity between any two subspace uploaded by any two local client. And this similarity will be used to indicate whether we should encourage to auxiliary model parameters to be similar when we run the personalized federated learning algorithm. Well, and in this case, in this page, I wanted to share more details about the client update. And so for the orange box, this corresponding to the objective function for each local client, say local client K in this case, how to learn how to update the local model parameters theta K. In this case, first of all, this client will receive the source knowledge, this auxiliary model parameter theta head K from the central server. So the question is that how can we encode this knowledge during local training? And basically this auxiliary model parameters corresponding to the source knowledge, which encodes the other relevant information from other clients. And in this case, we see that it's controlled by another hyperparameter, this lambda k. If lambda k equal to 0, we see that the second term will not be working. We see that it's just corresponding to the pure local training. without using any knowledge from the received from the central server. So in this case, a proper hyperparameter lambda k can help us mitigate negative transfer, because in this case, this hyperparameter lambda k will determine whether this client k, will use the received knowledge. So to determine the value of lambda k, we consider very simple intuition. That is, whether the received knowledge, this theta hat k, can help improve the generalization performance compared to the local model parameter theta k. And the next key component is the server updates. In this case, so after local training, each client will upload the personalized model parameter theta k to the central server. So the central server will do the model aggregation. This aggregation process will allow to each client have the corresponding relevant knowledge. Say like if only when two clients have similar data distributions, they will have more chance to get the similar auxiliary model parameters, in which in this case, the auxiliary will also allow that those two clients have very similar local model parameters. And if we check more details about this object function, we see that it has a very simple intuitive solution, which is given by the blue box. And from this iterative solution, we see that for each client, especially, for example, this client K, is corresponding auxiliary model parameters. It's just adaptively aggregates the knowledge from other clients. And this adaptive strategy will be determined by the distributional similarity between the target client K and the source client K prime. Say like corresponding to the term W sub K prime. If this term is large, that means client K and K prime are similar in data distribution, so that K will aggregate more knowledge from this source client K prime. And also for simplicity, we also show that this iterative solution has a corresponding closed form solution. And this also, basically this closed form solution can also be found in personalized page rank. The key intuition is to guarantee that only when two clients have similar data distributions, they will have the parameter propagation. Say like the client K will receive the knowledge from K prime only when the W sub K prime is very large. And then next, we show that how the proposed method will perform on real-world data sets. Specifically, we consider several different federated learning benchmark and compared our method with several baselines, including both global federated learning algorithm and several different types of personalized federated learning algorithm. And regarding the evaluation metric, in addition to the standard accuracy, we also report the relative accuracy and the positive transferability ratio. For the relative accuracy and the positive transferability ratio, we can see that in this case, we compared the accuracy reported by the personalized federated learning with the accuracy given by the local training to see that whether the personalized federated learning can really help improve the model performance compared to simple local training. If not, we will see in this case, negative transfer happened because the transfer knowledge in the personalized federated learning framework cannot help improve the generalization performance. So in this page, first of all, we can see the scenarios that clients have the same number of training samples. And we report, like we mentioned before, we report the accuracy, relative accuracy, and the positive transferability ratio. The higher positive transferability ratio indicates that the negative transfer will not happen. And from the right-hand side table, we can see that the proposed method, this Fedora algorithm can achieve comparable accuracy with the baselines, but it can consistently outperform the baselines in mitigating the late transfer issues. And more details, we check that when in the imbalanced setting, say like one client has a very large number of training samples, we see that what will happen for the personalized federated learning performance. And in this case, we see that after using the personalized federated learning, we see that this client, client 18 with large number of training samples, can easily suffer from late transfer because in this case, this client 18 has enough knowledge regarding from the training samples. That means that it's not necessary for this client to borrow knowledge from other clients. So that's why when it encoding the knowledge from other clients, it has large chance to suffer from late transfer for the federated learning framework. But the good solution is that our proposed Fedora method can avoid this late transfer in this case. And the second observation is that when the clients have similar distributions with this special client, this client 18, basically those clients can benefit from federated training because for this client, they are easy to borrow some useful knowledge from this powerful client 18. So that's why also federated learning method can get pretty good generalization performance compared to local training. But on the other hand, if the clients have different distributions with this special client, it also happens that negative transfer can happen in existing baselines. And our method, this Fedora method, can avoid the negative transfer issue because it will aggregate the model parameters according to the data attributes. That means it will only encode the knowledge from the clients with similar data attributes and drop the knowledge if the clients have totally different data attributes. So finally, we also report the communication cost and the computational efficiency. We see that this Fedora has comparable communication cost with the standard Fed averaging, and also regarding the computational efficiency, this method can also be efficient compared to other client relation-aware personalized federated learning algorithm. So basically, this is all about this paper. And in addition, I would like to share more about this topic, especially how can we encourage the positive transfer in the transfer learning setting in a trustworthy method. And well, this basically my research scope named trustworthy transfer learning. Here is a very generic problem definition, like when we have two domains, the source domain and target domain, how can we learn the reliable and trustworthy input-output relationship in the target domain? By using the knowledge from the source domain, like we discussed in the previous paper, like for each target client, when we have the data privacy constraints, how can we always borrow the trustworthy knowledge to guarantee that we can really improve the model performance in the target client? And there are two major challenges. One is the data heterogeneity, like the different domains could have different distributions. In this case, it requires that the knowledge can only be transferred when source and target domains have similar data distributions. The question is that how the transfer can be done in different trustworthy concerns, like the data privacy concern we discussed in previous paper, and also it's possible to involve other trustworthy concerns like the adversarial robustness, the fairness, and the transparency. And this corresponding to my research works, like I would like to dive into the trustworthy transfer learning from two different perspectives. One is the transferability, like how can we design the transfer learning algorithm to improve the generalization performance on the target domain by using the relevant knowledge from source domains. The second one will be the trustworthy case, like how can we design the transfer learning algorithm when we have the trustworthy concerns like the robustness, the data privacy issues. And basically regarding the knowledge transferability, there are two different scenarios. Like in the standard IID case, for each domain, like source or target domain, samples can be considered as the IID data. They are independent and identically drawn from the same data distribution. But for the non-IID case, the graph mining task, basically this corresponding to that for each domain, the samples could be connected with each other. In this case, how can we make sure that source and target follow the similar data distributions? And how can we design the transfer learning algorithm using both the simple knowledge and the structural knowledge? This will be the key question we want to answer in both IID and non-IID transferability case. So yeah, about the trustworthy, in addition to the data privacy we stated in the previous paper, we also care about the adversarial robustness concerns and also the fairness. Especially in previous paper, basically, we want to avoid the negative transfer for each client, which corresponds to a very special performance fairness, because we want to guarantee that other clients can benefit from the federated training. But a more generic definition about the fairness is that it's about the algorithm fairness, say like whether the fairness can be guaranteed individually or in group manner. Say like when we train a model, when we train a fair model in source domain, whether it can be guaranteed that this model is also fair on the target domain. This is also the issues we want to answer in this framework. So the overall goal or the future version for my research is to also get to understand the trade-off between transferability and trustworthiness. For example, it's already found that in standard supervised learning, robustness, fairness, or privacy can be added up with the prediction accuracy. That means when we improve the trustworthy properties, basically the accuracy can be degraded to some extent. So the question is that how can we achieve the best trade-off between the transfer performance and the trustworthiness properties in the context of transfer learning? Well, that's basically what I want to share in my talk. And well, I would like to take any question you may have.